This is an example of a problem where you can use a free body diagram to solve it. So if the question is, a 70 kilogram person, who I drew here, pushes a 700 kilogram car, which I drew here, with a force of 200 newtons. So there's a force, he's pushing here with 200 newtons. What is the car's acceleration? The first thing we have to decide is, what are we going to use as our system? What's the thing that we care about, the thing that we have a lot of information about? In this case, it's the car. So I'm going to consider just the car. So I'm going to draw a free body diagram for the car. What are the forces acting on the car? Well, we've got one. There's that 200 newtons. So there's 200 newtons here. And it should have a label. We've only got, there's normal force, tension force, gravitational force, and frictional force. What kind is this one? Well, it is a normal force from the person. So you can call it normal from the person. That's an option. You could also call it just some applied force. A lot of times there will be questions that ask, what is the force applied to do this? You can just call it force applied. So normal for the person or force applied. My preference will be to call it just an applied force. So I'm going to get rid of that just because I think there's going to be another normal force, and I don't want to have two normal forces to deal with. Is there a normal force on this car? Well, it's sitting on the ground, so there should be a normal force coming up from the ground because gravity's pulling it down, right? So there's an mg. I've tried to draw n and mg about the same height because I know the car's not accelerating this direction. Just from this problem, it doesn't specifically say the car's not floating away or sinking into the ground, but from my experience, I would say probably it's not. So normal force and gravitational force, equal and opposite, don't cancel out, and an applied force that way. Then we do, let's see, knowns and unknowns. Knowns and unknown. I know F applied. I know the mass of the car. I know the mass of the person. I know, wow, that's all we're given. All right. I also know gravity. Gravity might be important. Unknown, what we're looking for is the acceleration of the car. So if we're looking for acceleration of the car, we are going to want to use F net for the car equals m of the car, a of the car. So acceleration of the car. The acceleration of the car will be in this direction. I'm going to call this the plus x direction. So the acceleration of the car, that vector, I know it's going to be in the x direction. So ax for the car equals the F net in the x direction on the car over mass of the car. So what is the net force in the x direction? Well, there's only one, right? This one and this one. When we add the forces together, usually you break them into components, add the y directions up, that's the y direction one, add the x directions up. The only thing that we care about is the x direction. So this one doesn't matter, that one doesn't matter. The net force in the x direction is 200 newtons. So that's 200 newtons over mass of the car, 700 kilograms. So acceleration in the x direction is 2 over 7, or 0.286. Its acceleration, it should be meters per second squared. It's actually newtons per kilogram. So Newton, 1 Newton is 1 kilogram meter per second squared. So a kilogram meter per second squared divided by a kilogram is a meter per second squared. So there we go. we solved it.